All right, for geometry today, we're doing 7.2, areas of other quadrilaterals. So we kind of just have one objective today, and that is to apply the area formulas to find the areas and lengths of trapezoids, kites, and rhombi. Okay, so a little bit different. So we're going to start with three theorems and go through those because they're the theorems with the formulas, and then we'll do some examples. So first up, the area of a trapezoid, okay, so we've also got a picture here, is 1/2 the product of its height. So we see that here, 1/2 the product, and the sum of the lengths of its bases. So that's what we've got in parentheses, the sum of its length of its bases. It doesn't matter if B1 and B2, like which one you put where, okay? Just the fact that there are two different length bases in a trapezoid. And then the height is always perpendicular to the base, right? It's that line there you see is the height. Okay, next theorem, the area of a kite is 1/2 the product of the lengths of its diagonals. So we've got that formula here. It's half of diagonal 1 times diagonal 2. Again, it doesn't matter which one you consider diagonal 1 or diagonal 2, just that they're there. And it's the same formula, if you notice, if you look for the area of a rhombus. Okay, is the same. It's 1/2 the product of the lengths of diagonals. So in this one I add a little more detail. We have diagonal 1 and diagonal 2, but I also put a measurement because remember in a rhombus the sides are equal, but the diagonals are not congruent. So I always want that kind of maybe will help you remember that the diagonals of a rhombus are not congruent. So that's why I put that in there. But they have the same formula. The area of a kite, the area of a rhombus are the same formula. And then the area of that trapezoid is the 1/2 the height times the sum of the bases. A little bit different up there. Okay. All right, so let's get started then with the examples. Okay, example 1 says find the area of each side of the popcorn box if the sides are 6 inches tall, its top edges are 4.25 inches, and its bottom edges are 3.25 inches. All right, so it looks like the top, okay, the top here is 4.25 and the bottom is 3.25, so it's a little bigger on the top than it is on the bottom, right? So 4.25 versus 3.25. I feel like my 3.25 is a little narrow. Okay, and then it's 6 inches tall. So if we connect this, and it's 6 inches tall. Perfect. So this is what shape? Is it a kite? Is it a rhombus? Is it a trapezoid? Trapezoid. So we need to use the formula for area. So area equals 1/2 the height times base 1 plus base 2, the quantity of base 1 plus base 2. So let's plug in numbers. 1/2 the height, which is 6, times the quantity of our bases. So one base is 4.25 plus the other base, 3.25. All right, so that's going to give us area equals, I'm going to go ahead and do 1/2 of 6, which is 3. And then 4.25 plus 3.25 is 7.5. So the area is 3 times 7.5, which is 22.5 inches squared. Remember, area is always inches squared. Always. But today's going to be that rock star day where we're just using the formulas kind of and plugging them in and solving. Okay, a day you've wanted since like Algebra 1. Okay, so let's look back to example 2. Find the area of the kite. All right, awesome. So this time our formula for area of a kite is 1/2 the product of diagonal 1 and diagonal 2. So our area equals 1/2. One area, now if we look at this, is, we look at our measurements, we've got 13 and 30 centimeters, and then the other one is 115 millimeters and 115 millimeters. So they've given us the dimensions for both of those. Okay, but they're in different units. That kind of stinks. So let's take this 115. Let's find what's the length of this whole diameter then, or diagonal, pardon me. It's 115 plus 115. That would be 230 millimeters. So let's change that to centimeters, which would be what? Should be 23, right? Because 10 centimeters or 10 millimeters equals 230 millimeters. All right, so let's go back here. So we're going to have 1/2 of 23 times. Now let's look at the length of our other diagonal. If it's 13 centimeters and 30, we add those together, that's going to be 43. All right, because we did 13 plus 30 equals 43 centimeters. We'll get that in there. Okay, so our area is going to equal 1/2 of 23 plus 43. 43 times, hold on, 1/2 of 23 times 43, which is 494.5 centimeters, what? Squared. Excellent. 494.5 centimeters squared. Now, the other thing, you could have converted the centimeters to millimeters and found it that way. Doesn't matter to me either way. It didn't specify in the question, so I would take either unit of measurement in this case. All right, let's look at example 3. Find the height of rhombus ABCD. Now, time out. That's a little different. Find the height of the rhombus. Well, intriguing. We have the dimensions of the diagonals, so we could find the area. But if you also think back to yesterday, okay, we found like a rhombus is a parallelogram. So here's some things to think about. A rhombus is a parallelogram, and we know to find the area of a parallelogram. That looks like a trapezoid and not a parallelogram, so there we go. Make it more parallelogram-like. Equals the base times the height, where the area of the rhombus is 1/2 diagonal 1 times diagonal 2. You can use either of these, technically, because a rhombus is a parallelogram. In this case, though, we're going to have to use the second one because those are the dimensions we know. Okay, we know the diagonals. But once we know the area of the rhombus, we can use this one. I'll mark it number 2. We can use it next, and we'll have the area. We have the base length down here, so we could plug it into the formula, and then we could use and solve for the height. So that might seem a little wonky, but we're going to do this one first, find the area of the rhombus, and then work backwards and find the height, okay? Because we're going to use the information that we know. All right, so here our area is 1/2. One of our diagonals is 4 meters, so 1/2 of 4 times 3 is our other diagonal. Okay, so our area equals 1/2 of 4 is 2. 2 times 3 is 6. So this is 6 meters squared. That's helpful. But we're not done yet. We got to bring this to this part over here, to this equation. So now we're going to have the area is 6 equals our base. Okay, our base is this 5 meters here. That's the base length. So 6 equals 5 times the height. Pretty sweet deal there, right? Okay. And so we divide by 5 on both sides, and we have 6/5 equals the height. 6/5 meters, or 1 1/5 meters. Oh, you know what? Yeah, I'm good with that. It depended, I guess, on how we looked at this. When I read these measurements, I took 4 meters as the whole length. So I want to clarify that. I took this 4 meters as the whole length of this diagonal, okay? And 3 meters as the whole length of this diagonal. So we'll have to clarify some of that on our notes. So if you're working through your homework and you get an answer that's a less than or different, you might look back and see how they calculated it. If you just interpreted your drawing a little bit differently, I will understand that. Because sometimes the book makes it like this whole thing is 3, and other times it makes it like just that from the mid segment to the edge was 3. So if that confused you even more, I apologize. But if you were like, wait a minute, this should have been 6 and 8, I get that, and we can talk about that some more in class tomorrow. Because it could be, I could see where that part is confusing, and we can talk about those some more. So, all right, let's move down to example 4, our last one. We want to find the area of the quadrilateral WXYZ with W at 4, 1, X at 1, -3, Y -2, 1, and Z 1, 5. So I've already drawn this shape up for you so we could save some time, but we want to find the area of this quadrilateral. All right, so gotta kind of figure out what shape this is though. That's kind of problematic. Kind of looks like maybe it's a rhombus, so, or maybe it's just a parallelogram. We don't know if they're parallel though, unless we find the slopes, but we can also think, like, let's check this out. And let's connect and get a diagonal in there. Okay, so there's one diagonal, and here is another diagonal. Just by drawing those, what do you know about the diagonals? All right, they are perpendicular. Right? These diagonals are perpendicular, which confirms that this is a rhombus. Right? So because we know it's a rhombus, so let's make a note here. So it's a rhombus because diagonals are perpendicular. So see those things we didn't know, you know, like these theorems we've been learning and these postulates? They're super helpful even in coordinate geometry. All right, so we know it's a rhombus because the diagonals are perpendicular, which means we can use the formula A equals 1/2 diagonal 1 times diagonal 2. All right, that's going to save us a lot of work. Okay, because then we can count our diagonals. Okay, so this diagonal from WY is 1, 2, 3, 4, 5, 6. So we can put W, or YW, pardon me, equals 6. And if we do XZ, it's 1, 2, 3, 4, 5, 6, 7, 8. Okay, so XZ has a length of 8 for the diagonal. So our area is going to equal 1/2 of 6 times 8, which means our area equals 1/2 of 6 is 3, and 3 times 8 is 24. Okay, remember it's area, so we're going to put units, because we don't have any other measurement, squared. All right, so in that coordinate geometry, this is the key there. Still use the things that you know about the different shapes to help you determine what kind of shape it is. You may have to find the slopes of the lines in order to know if it's a different shape or not, like in a trapezoid in this case, or in the case of this one with it being the rhombus, we check the diagonals. But if you want to know if it's a square or if it's some other shape, you can check some of the other rules. You might have to find use the distance formula to find the lengths of your sides. You might have to use the slope formula to find the slopes to see if things are perpendicular, if the intersections didn't work out perfectly like ours did, because sometimes they won't. All right, then you are ready to get started on your homework. Have a great day. I'll see you tomorrow.